In this video, I want to talk about vector functions as position functions, in which case the derivatives become velocity and the second derivatives become acceleration. This is very much like what we had back in Calc 1, where you were just describing motion along the line, and the function was telling you where on the line you are at any point in time. Right? The independent variable was time, the dependent variable was position, location, measured in inches or miles or some unit of distance. Right? And so then the derivative of distance would be the rate of change in the distance with respect to the independent variable, which is time. So it's miles per hour or feet per second, which was the velocity. Right? And then the second derivative would be the rate of change in the velocity, which would be acceleration. Now we have a very similar thing with vector functions. If the independent variable is time, which is why we usually use t, then the vector function r of t represents a location not just along a line, but some location in space. If you're using r of t as x of t, y of t, z of t, or if it's just in the plane, it's just x of t, y of t. But you're describing a curve either in the plane or in space, right? And the position function is precisely that. It's where are you with respect to time. Each of the three components, x, y, and z, are measuring a distance along that particular component, right? So if x is measured in inches and y is measured in inches and z is measured in inches, then when you're at the point 1, 2, 3, that's 1 inch over, 2 inches that way, 3 inches up. And so the derivative then would be the way you take the derivative of a vector function is take the derivative of each piece, right? Each component. And so you'd be, in the first component, you'd be doing inches per whatever unit of time is, inches per second. And then in the y, it's inches per second, and the z is inches per second. Each of those is inches per second. So the derivative of the position function becomes something that contains all information about velocities. Velocity in the x direction, velocity in the y direction, velocity in the z direction. And the total vector is the velocity, right? It gives you all the information you need to know in each of the directions. So if r is a position vector, then r prime of t will be the velocity vector. And likewise, the second derivative would be the derivative of the velocity. So the rate of change of velocity is the acceleration. But these are now vectors. It's not just speeding up along a line, or for velocity, how fast are you going along a line, or the acceleration is how is that velocity changing as you move along the line. You're now saying as you move along in space. So your velocity being a vector is not just telling you how. When we're doing it with one variable, the velocity, you had a plus or a minus. So you're either moving this way or you're moving that way, right? But now you could be moving in any direction, and the velocity vector will be pointing in the direction that you're moving. And it turns out that the length of the velocity vector is what we call the speed. So the velocity tells you information about direction of motion and how fast you're moving. Now, let's do an example here. R of t is sine 2t. It's my example. Take the derivative, cos t, 2 cos 2t, remember the chain rule there. And the acceleration vector is the derivative of the velocity vector, which is the second derivative of the position vector, minus sine t minus 4 sine 2t. Now, I mean, it's easy enough to take those derivatives, but what does it mean? Let's look at it geometrically. Let's look at a couple of graphs here. So the first picture that I want to show you here is this one. We have the same vector function as we just did as an example here, sine t sine 2t. The velocity vector is described as the derivative of the position vector there. So in blue, I have both a blue dot and a blue vector. In red is the velocity vector, and in green is the curve described by the velocity vector, right? I mean, each time you take the derivative of a vector function, you get a different vector function. And so it's interesting, I think, to view this in a couple different ways. So if I click on this to animate it, I can see that the two red vectors are the velocity vector, one based at the origin and then one moved out to be on the, have its initial point on the curve there. And so you can see that from the one base at the origin, that the velocity vector is tracing out a curve of its own, right? But that it's related to the original curve because it is always a tangent vector to the original curve at the point on the curve that the original vector function is describing. So you can see it move. And you can see how, like as it passes through the middle right there, and right here, the position vector and the velocity vector are lined up pretty closely there, and it's just moving along that straight line. It's not bending. It's not bending left or bending right, but when, at a position like this, where the velocity vector is pulling this off to the side, then that's going to cause this to start turning here. It's almost like the velocity vector is just tugging this thing around, and we just crashed. Time for the next picture. So this picture now is very similar to the last one. It's the same vector function. You can see the vector drawn here in blue. In red now is the velocity vector, and green is the acceleration vector. If I set this in motion, you can see different things happening. But again, I think in this representation with everything based at the origin, it's hard to really see what the velocity and acceleration vector, what the significance of them, right? So let's stop this and move that. So I'm going to pick them both up and place them, rather than being based at the origin. See, the blue one is V. So I'm going to put this at V. And you can see that our red vector just jumped up to be based here at the tip of the blue one. And then I'll do the same thing with the green here. Okay. And so now, when I animate this, you can see the red vector is the tangent vector, and the green vector is somehow, boy, it almost looks like it's kind of a spring that's trying to pull on that blue vector, right? Like now it's pulling up really hard, and so the blue vector starts going up, and now it says, no, come back down again, and no, go back up again. And then no, go back down again. So it's tugging it. It's at force. It's the acceleration vector. Now, for as interesting as that is, actually, there's one more thing I want to say about this. So take a look at a position like this. The acceleration vector is almost in the opposite direction of the velocity vector. So this should be meaning that this is going to slow down. That the thing's trying to move that way, but it's being accelerated in the other direction. Right? And so I'm going to get back to that spot here. So there's a couple of different situations here I want to take a look at. And that is like at this point right here. The acceleration vector is almost perpendicular to the velocity vector, which means it's not pulling it forward. It's not speeding things up. It's just causing it to turn, right? So at this stage right here, as we pass through this corner, it's like it's not speeding up. It's just turning. The acceleration vector is just causing the velocity vector to change direction, not length. So when I click on this, it isn't getting faster or slower. It just changes direction. Right? So it just goes through there. It's fairly constant speed around those corners, and this just keeps crashing. So one last thing I want to try to do here, I say try because the software keeps crashing on me. I love this software for its ease of putting together graphs, but it's riddled with bugs. Anyway, I've moved the acceleration vector out to be at the point here. All right, watch what happens when I set this going. Okay. What I see is that the blue vector is being tugged around by the red vector, but the red vector is being tugged around by the green. Each is the derivative of the previous one. Right? So the green vector is causing the red vector to change. When it's up like this, you can see the red vector is trying to go up, but the green vector is saying, no, no, come down. And so the red vector starts to come down again. But as soon as it does start coming down, the red vector says, no, 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 go back up again. And there's also a matter of the green vector pulling it to the left and to the right. That keeps tugging that velocity vector back and forth. And so as that velocity vector is being tugged around, it's tugging the blue along in its wake, right? That it says, oh, okay, well, I'm going this way. And the blue vector says, all right, I'll follow along behind you. Right? Each derivative is causing the previous one to change. Right? The red is causing the blue to change. The green is causing the red to change. And the net result is creating this figure 8 path. Now you could also take more derivatives. You could look at the third derivative, which we would call the jerk, and the fourth derivative, which, well, it's the rate of, it's the change in the jerk, which I call an election. Anyway, there you go. There's some visualizations of acceleration and velocity with vector functions.